this is a very interesting problem because it illustrates that sometimes you want to introduce an ordered relation and you introduce something that looks natural. I mean, seems natural to interpret that as an ordered relation, but some property fails. In this case, it's going to be anti-symmetry. And then it illustrates a way to remedy this problem, right? So let's begin with the first item, and we're going to show that if you have a set, in this case is the set of the Cartesian product of positive numbers, positive real numbers, right? Then one pair is related to another pair if and only if this product satisfies, these two products satisfy this relation. But there's a better way of writing this. Since both are positive numbers, then we can divide by the product y1, y2, the whole inequality, and then we end up with this. So that inequality is equivalent to this one. And now it's more clear what this means, right? So what we have to do is to calculate what is the ratio between these two numbers, right? And the ratio between these two numbers, and if this ratio is larger than this, larger than or equal to this, then they are ordered. Well, that's what we want, right? Okay, this is clearly reflexive, right? Because x over y is smaller than or equal to s over y, okay? And it's also transitive because if x1 over y1 is smaller than or equal to x2 over y2, and this one is smaller than or equal to x3 over y3, then of course this one is smaller than or equal to this one, right? So it is reflexive and transitive. This is no problem. The problem is anti-symmetry, and the reason is this. Suppose that you take, as the first pair, you take 1, 1, and as the second pair, you take 2, 2, right? Then 1, 1 is smaller than or equal to 2, 2, right? So you can say that R1 is 1, 1 is related to 2, 2, like this. And the reason is these ratios are both 1, so they are equal. So they satisfy this relation. But since they are equal, they also satisfy this relation. Okay? And this relation says that 2, 2 is related to 1, 1. So now you have two different pairs, two different elements, so that one is related to the other and the other is related to the first. And that is impossible, right? Because anti-symmetry requires that if this happens, the two elements are the same, but clearly the two elements are different. This is 1, 1 and this is 2, 2. They are different, right? So it's not anti-symmetric. And therefore is not an ordered relation. Not an ordered relation. Okay, so but what is going on here? Well, clearly the defect is something that we don't want to take into account really, because for us this fraction and these fractions represent the same number, right? It is all that matters here is what is the ratio between these two numbers. So what we're going to do is to introduce an equivalence relation in this set that groups together all fractions we have, or all pairs that have the same ratio, right? So if we do that, then this pair and this pair, this pair and this pair will belong to the same class, and we're going to work on classes, right? So this is item B, and this is the order, the equivalence relation that we want to define. Okay. So this is B. So the equivalence relation we're going to define is this: x1, y1 is related with this equivalence relation to x2, y2 if and only if the ratio of the first and the ratio of the second are the same. Okay, or if you want to put it in the same way as we put this order relation or the alleged order relation, then what we will say is that x1 y2 is equal to x2 y1. Okay, Right. This is clearly an order relation because this is a function of the first pair, and this is a function of the second pair. It's actually the same function, right? And when you have a function which, and you define a relation in this way, so that the function of the first pair is equal to the same function of the second pair, then this is automatically an order relation, right? So we have this order relation, and the next thing to check is what are the order, equivalence classes of this, right? Well, clearly the equivalence classes are going to be all the pairs of positive numbers times r plus, such that the ratio is constant, is the same, and well, this is equivalent to say that x is going to be r times y, okay, and r is fixed. It's a fixed positive number, right? Well, clearly one representative of this class is just r1, right? Okay, this is one of the pairs that satisfies this relation, right? But any other belongs to the same class. And now once we have these classes, now we can recover our original relation, but now this time not applied to directly to pairs, but directly to classes. So in other words, what you have now is this relation. You have one class, and you have another class, right? And you say they are related if and only if R1 is smaller than or equal to R2. All right? Okay, let's see. Well, we don't have to check reflexivity and transitivity because they are warranted. They were warranted before, so they are warranted now. The only thing that we now have to check is whether this is antisymmetric. And let's see. Antisymmetric means that if you have this and you have also this, okay, which according to this would be this, then what you have is actually that R1 is equal to R2, which is true, right? If you have, for two real numbers, you have this relation and you have this one, then automatically you know that this must be the same. And if they are the same, then these two classes are the same. So R1 is equal to R2. R2, 1. And this is antisymmetry. So now on this set of, on this quotient set, right, on the quotient set, R plus times R plus with the equivalence relation that we have introduced, right? Now this relation or this correspondence that we have defined, R, is an order relation. You see? So with the equivalence relation, you remove the problem that you have before, that you have different pairs having related symmetrically, right? Okay, now the last part is we need to prove, now that we have this, that this quotient set with the order relation that we have defined, the extension of this, is a totally ordered set. But this is trivial. It's a totally ordered set because the order relation is given by this, right? It's the order relation of these first elements. And then, and this, for real numbers, this is a total order, right? So we have a total order. Given two numbers, so given two classes, say R1, 1, and R2, 1. Okay, these are two classes of the quotient set. Either one is smaller than or equal to the other. So if this happens, then this class will be related to this class. And if the opposite happens, then it is the other way around. It's this class that is related to this class. Right? So given two elements of this set, either this happens or this happens. And that's exactly the definition of a total order, right? And this is true because for two real numbers, either this is true or this is true, right? Of course, if they are different, okay? One of them is true and the other is not, okay? So this is a total order.